making me a host. Okay.
Okay. All right. Hello, everyone. Welcome to the reading group. For today's reading group, I'm going to present basically two topics, Gaussian process and determinantal point process. So for the content I'm about to present, I will majorly follow Eric Xing's lecture, which we have been following along the way. But more than that, I will also show some slides I took from Richard Turner, who used to work at the University of Cambridge. And then I think from Professor Turner's slides, there are more motivating examples and better visualizations for us to get an idea of what's going on of Gaussian process. And Gaussian process is going to be the major focus today, probably take most of the time. After that, there is a second topic called the determinantal point process, which I took slides from Peng Taoxie, who used to at CMU and right now a professor at UC San Diego. So outline will be like this. We will spend most of the time talking about Gaussian process, and then we will give motivating examples of a Gaussian process. And then we discuss some concepts like parametric models versus non-parametric models. And then we talk about the definition of Gaussian process, how do we do inference and learning. And then finally, we talk about two relatively recent applications or like research ideas. One is that people actually combine deep neural networks together with Gaussian process, which result in this paper called deep kernel learning. The other one is actually I added there, I found more relevant to our group because it's a combination of graph convolutions and Gaussian process. It's published in ICML 2019. So after that, we will go over the idea of determinantal point process. For both of these two topics, compared to the other topics we have seen in graphical model, the major difference is that we now are going to define these distributions not just on random variables anymore. If we recall, we talk about graphical models, we usually define like random variables in our model, like X, Y, and Z. And then we want to have a distribution defined on these random variables and sort of do the learning and inference starting from there. So for Gaussian process, we are actually going to define a distribution on functions. And for determinantal point process, we're going to define a distribution on sets. So both of these two objects are sort of special objects beyond the traditional simple random variables. We will be more precise when we get to the actual definition of what's going on. So, okay, let me start with the Gaussian process then. So I would like to start very gentle with this super simple idea. So hopefully through this super simple idea, you are able to at least intuitively get what's going on with Gaussian process and why do we want to use Gaussian process. Let's just consider this very, very simple example that like one-dimensional linear regression problem. I have an input X, and then I observed some corresponding Y, like the red points showing on the screen. And the question I want to ask is that for a X I have never observed, can you tell me what is its phi value, right? This is like a super simple problem. You probably have seen it in your first course of undergrad machine learning. And then, so maybe we can consider a linear model fit to this, right? Then it will just be a linear regression. But apparently, based on these 5 points, we can see the relationship is not that linear. So we may consider something a little bit more complicated, like a nonlinear regression. You probably expand your basis to be polynomial basis, or you introduce other nonlinearities. But at the end of the day, you want to get a sort of a curve, looks like this blue curve on screen, trying to fit this blue curve to these red points. So when I ask you the Y value of a new X, you should be able to read that out, right? So probably I ask you, what is this x value corresponding, the y value corresponding to this x value? I can just check my curve, and then I see, okay, the prediction is right there. Well, what's more than that is that we can actually come up with our confidence score of this simple prediction problem. So in this case, not only fit a curve there, but I also have this interval associated with each point on the curve. Still, if we take this example, right now, if you ask the same question, I can tell you this is my prediction, but I can also tell you, well, my prediction might range between this interval, right? So I'm not that confident enough about my prediction. I tell you that all of these values are sort of possible predictions. This is actually something that the parametric model, or let's just say neural network, which we use most commonly used these days, what neural network usually cannot do. Maybe there are some very special modifications based on neural network can give you confidence predictions as well. I know one line of research going on called Bayesian deep learning. But most of the case, the plain neural network cannot give you this uncertainty estimation, cannot tell you how confident I am about my prediction. So maybe like in this area, right, because I observed too many samples, I'm fairly confident that I'm almost like completely sure about my prediction. But for other cases like this range, right, I have actually never observed any data point between this range. So sometimes, besides the prediction, I would like to know my confidence as well. Like the real life applications may include, say, self-driving cars. For this kind of very critical tasks, when you want to determine you want to turn left or right or go straight of your car, sometimes you want to know the confidence score as well, right? You only want to make very confident moves. Otherwise, that may cause car crash and life-threatening accidents. So the model we're going to introduce today actually has this ability to give you the confidence prediction other than the simple result. That's the Gaussian process. So Gaussian process, right, is already called a Gaussian. So we are wondering to fit this kind of curve together with this confidence score, can we do all of these things just with a Gaussian distribution? This is a question we ask. And then I assume everyone here, we are super familiar with the Gaussian distribution. So we won't do a review. We will directly look at a Gaussian and then do a look at some properties we're going to use today. So here I'm showing a two-dimensional Gaussian on the screen with its analytical form of the distribution and then a contour plot of the Gaussian. For simplicity, I will just assume there is no mean parameter. So basically, the Gaussian is centered around 0. And then in this case, all the parameter we have in this Gaussian is this covariance matrix. So as long as I know this matrix, I'm able to specify the whole Gaussian distribution. And these black points are just showing some examples I got from this Gaussian distribution. Another nice thing about Gaussian is that even though I'm looking at a two-dimensional distribution, if I do this kind of projection or I conditional on one value of its first dimension, like equivalently, like two equivalent things in this context, I will be able to say that the conditional distribution of the second dimension or the projection on this line is still Gaussian. So it looks like this. In this case, how do I read this plot is like the following. I fix the value of y1, and then if I sample from this Gaussian, all the points I get are going to be projected on this red line. So I might get some points here, 1 point here, maybe 1 point here, and 1 point here. But if I look at the distribution of all these blue points I sampled as the projection on y1 equals 1, then I will get their distribution looks like this red curve. So it is still Gaussian. In the middle, it's more likely to get sampled, while on the two tails, it's less likely. So this is actually really nice. see that the whole idea of multivariate Gaussian process is based on this nice property. And then in this case, when we consider the conditional distribution, we will get two new parameters. One is this parameter mu star, which describes the mean of the projections on this red line. One is this new covariance matrix sigma star, which describes how spread this new conditional Gaussian is, right? So, and then it will be looks like this. We will see that this mu star is just a linear function of this y1. Later on, we will give a precise formula for what this w is, but it is a linear in y1. The formula for the sigma star is slightly more complicated. We will also see the exact formula, but we will see both these two parameters are just the sum functions based on the original parameter sigma and the y1 value u conditional. Okay, so this is the multivariate Gaussian distribution and the conditional distribution of the Gaussian. Right now, I would like to introduce a new way to visualize this whole thing, so we can sort of see what is Gaussian process. Still, I have this two-dimensional Gaussian distribution. I have one covariance matrix specify this distribution, but right now I will visualize it like this. I take the y1 value, and then I just use its index 1 as the x-axis. I use its value, right, in this case 2, as the y-axis. Similarly, I will take the value y2 and then draw another point, x-axis equals 2, y-axis equals 2. So in this case, basically what I did was that I sample a point from this Gaussian distribution, right? So in this case, I sampled 2, 2, this point. And then for each dimension, I just listed it out, use the dimension index as the axis, but draw the values on the y-axis. Well, I can draw a slightly different point. In this case, I moved a little bit I moved a little bit towards this direction and this direction. So my y1 values get a little bit bigger, my y2 get a little bit smaller. I can draw another point where I move the point here, and then my visualization has also shifted down, right? So it used to be look like this. And then I can keep going. Whenever I draw a new point, I'm able to visualize this new point using this new visualization I just developed. And then I can also do something I just talked about, right? I can do this conditional visualization, meaning I fix the value of y1, in this case, the red point. This point is not going to change anymore, but I can move my sample up and down on this y2 direction. So I will be able to get a visualization that looks like this one, right? So if I move down a little bit, oh, sorry. If I move down a little bit, you can see this visualization also, the right-hand side also moved down a little bit, right? Let's compare these two visualizations. Okay, this is a new visualization I can do of this multivariate Gaussian, right? So I can further extend that to be more than two-dimensional. So in this case, for simplicity, I'm still showing only two-dimensional y1 and y5, but with this covariance matrix, you can see that I actually have 5 dimensions. And I list out these 5 dimensions, and it gives me a curve, looks like this one, right? The value of y1 through y5. Similarly as before, I can draw a new sample. I can expand the number of dimensions. When I get to a dimension of 20, and then I draw one sample from this 20-dimensional distribution, I'm able to draw a curve that looks like this, right? We can already sort of see in this case, we get a nice looking curve. And then this is what we want to go forward. We want to have more and more dimensions, and finally approaching a continuous distribution in this new visualization. So for this 20-dimensional setting, I can also do similar things as before. Maybe I fix 2 dimensions, right? This both y1 and y2, and then I draw samples so other dimensions will change in this case. And then these 2 red points will always be fixed here. Then if I do not do the sampling, I look at the distribution of this curve formed by these 20 points, I will see that, let me change to another color. I will see that in this case, for these points, right, which are close to the 2 points I observed, their uncertainty is actually quite small. Right, I need to expand this. So here, these dots, or maybe I shouldn't use red to confuse you with the observed points. Let me use green. So these dots represents the dimensions I never observed, but I use these blue dots to represent their mean. And then this bar represents also the standard deviation or the uncertainty of these points. So in this case, we can see based on this covariance matrix, for the points that are close to our red points, the observed points, its mean value is also close to these red points, right? The dots is close to here, and then the uncertainty here is also small, right? So if we look at the first three points in the covariance matrix, we see they are highly correlated. So knowing the first 2 points gives me a lot of confidence of saying, okay, what is the value of the third point? I'm less uncertain about where it should be. But if we look at the last 2 points here, compared like its correlation with the first 2 points I observed, it's like this small submatrix here, then basically they are uncorrelated. Observing these 2 red points tells me nothing about this the 19th and the 20th dimension. So they will just be the distribution they started with, meaning with mean 0 and the unit standard deviation, right? So that's in this case how we look at the distribution of the points we haven't observed. This is the slides I showed before. This is kind of a sample we draw from the distribution, right? So here, maybe when we draw samples in each dimension, I may get, okay, maybe these points, right? So, and then once I put them together, I will get this kind of curve. So the sample might look like this. And then, yeah, I guess I already talked about this. The meaning of the dots and the bars are the mu and sigma conditioned on the 2 points we have observed. Sometimes we may observe other red points, not just the first dimensions, right? Say we observe some dimensions in the middle, this gives us more certainty about what's going on, maybe in this area and this area, because we know points from both ends, right? And then if we want to go go higher dimension, the best way to do that is to use this so-called covariance function, because otherwise you get an n by n matrix, but it cannot allow you to go infinity, right? Because you only have 20 dimensions to store all the covariance scores. But if I define a function looks like this, then whenever I want to find the covariance between 2 points, I can just plug them in, and then I can read out a corresponding value, like how correlated these 2 points are. And then this kind of a covariance function, in our case, is specified by one kernel function plus some random noise. In this case, this kernel function, I think also most of us are very familiar with, we can think of it as like a similarity measure. If I compute the kernel between point x1 and x2, that basically tells me how similar x1 and x2 are. And then we have some random noise we want to add to this kernel value to allow more randomness. So this is just a hyperparameter plus the identity. Yeah, so with this kind of function, we can go to infinite dimensional. We think of the covariance matrix as like a—
Can you go back?
Yeah.
Here, what is sigma y?
Oh, okay. Yeah, sigma y is like one hyperparameter.
So what is that?
So yeah, so basically we want to specify this Gaussian distribution. So we want to specify its covariance. And for this covariance, we want to be able to compute the covariance for any two input, say x1 and x2. In this case, the covariance of x1 and x2 will be composed using these two parts. One is the kernel function. The other one is some random noise we want to include. So the kernel function is this one, but we want additional randomness there to for this covariance computation.
I see. So it's a diagonally we have the sigma y squared term.
Yeah,
And
yeah.
other terms are Gaussian distribution, normal distribution.
Yeah.
And it depends on the distance. What's the distance here? What is x1
which-
and x2?
x1 and x2 are two input data points. So let me see.
So they're indices?
If we no. If we look at this problem, right? So this could be x1 and this could be x2, and then we want to compute their covariance. So we plug these two values into the kernel function and then compute the covariance between them. They are not indices in this case.
So then what? Can you go back to the formula again? I just want to get very clear understanding.
Yeah.
So here, so at the end of the day, what we are getting is the covariance.
Oh, yeah. Sorry, I guess I maybe misspoke one thing. So in this graph, the x1 and x2 are indeed indices in this graph because we only have 20 points. I was thinking about like in the continuous case, they are just the real values on this line, the x1 and x2. Yeah. But please continue.
So covariance consists of covariance of two y values at the given. So these are the covariance of the y values, right?
Yeah, these are the covariance of the y values, but
And
they
x1
are
and x2.
Yeah, they are functions of x1 and x2. Yeah.
And when x1 and x2 are large, where the difference is big, far apart, then covariance becomes smaller.
Yeah, so if we use this particular Gaussian kernel function, and then yeah, when they are large, it becomes smaller. Yeah.
But they will never go to 0 because we somehow enforce this sigma y term there.
But this sigma y is only on the diagonal, right? So if we look at this entry, it can be 0, right?
Oh, I see. So it's more of a delta function then. That the sigma is the way. Somehow this formula, this overall equation is mixing up a lot of things. So I'm kind of a little bit confused about what this means exactly. So this one is almost like a delta function. So when it's the diagonal entries, the I term comes in and then it becomes sigma y.
Mm-hmm.
So that is where things are. I still don't understand why we need I.
So maybe when we get later when we look at I don't know which slide, I might have one slide can answer this question. But for now, to get an intuitive idea, we can think of it as purely the kernel function. Yeah, so I might have it here. Later on when we get here, we will see to specify the Gaussian process, we're going to have like one kernel function plus this I. This I is some random noise we introduced to the model. So to give a quick explanation, maybe look at this. So later on, we will do a prediction of y values based on x, right? And our prediction will be this blue curve in the middle, this fx. And then this fx itself contribute to this k function. And then the variance is the k function. But other than the k function, we want to include an extra randomness here, this sigma y. And I know this answer is pretty rough, but I guess we can talk more when we get there.
Okay, thank you.
Yeah. So if
I have a question here, just clarification.
Yeah.
So what are the variable index here? What do you mean by that? Are they the? I mean, before this slide, I saw that each variable index is kind of one dimension, right?
it is, yeah.
Right, but what are x1, x2? They're not the dimensions, right? They are the data points, or?
So yeah, thank you for the good question. Let me make this clarification. So we think of this variable index as dimensions when we give this motivating example with only like 2-dimensional Gaussian, 5-dimensional Gaussian, and 20-dimensional Gaussian, right? So, and then we can specify each dimension. For each dimension, we have like one variable index and one y value associated with this index. And then, but our goal is that we want to be able to model continuous functions, meaning on the x-axis, if we have infinitely many values, in which case we cannot use it as an index anymore, it's just a real value. We want to still be able to specify the covariance between any two values. So in order to do that, we define this function that takes in any two real values. So we will be able to generate a smooth function looks like this one, right? So we can input
So
any
how
x1 and
this-
x2.
So this x1 and 2 right, are really corresponding to 2 points, right, on the x-axis. Is that right?
Yeah, so if we are only looking at 2 points, we can still think of it as 2 dimensions. If we are looking at all the real values on the x line, we can think of it as infinite dimensional.
Right.
Yes.
So I'm trying to understand what's the relation between in your formula, right? It's sigma x1, x2, that x1, x2 with to this x.
Mm-hmm.
I guess I'm just confused there. Maybe I missed something.
So
Those x
maybe
are, it's different from this x, right?
Oh, you mean the x here is
Yeah,
different from the x here?
Uh-huh.
They are the same x, right?
They are the same,
Yeah. So okay.
but then this
So
x1 and 2 are not 2 data point, right?
let me draw this again. So let's say we just have let's say we just have 2 points. One is this one, x1, y1, right? One is this
Okay.
one, x2, y2.
Right.
Right. And then this thing, what this tells me is that I try to compute the covariance between y1 and y2. And then the way I compute it, the covariance between y1 and y2 is I plug in x1 and x2. And then according to this formula, I get the covariance between y1 and y2. Is this clear?
Okay. Oh, that's how you mean x and y. Okay, that's what
Right,
you mean
right.
by the data point. I mean, I saw that there was like the original point in a few years back, a few slides back, where each one actually corresponding to a curve. So you didn't mean that point, okay? You mean point in this 2D plot, right?
Yes, yes.
I see, okay.
Yeah. Yeah, sorry for the confusion. I hope everyone gets what's going on clearly. So for all of this covariance modeling, we are modeling the covariance of the y values, right? So So we want to know that on the y-axis, like how, maybe I go back to this, right? I want to know how big, how these points are correlated, so I can figure out the influence by this red point to this unobserved blue points, right? So if let's say these three are very highly correlated, and then once I observe these two, I can very confidently say what's the position of the third one. So that's what we want to figure out. But to calculate that, the way we do the calculation is that we take the corresponding x value and plug it into this formula.
May I make a comment here?
Yeah, please.
Yeah, personally, I think if we consider this curve is a time series, that's going to be easier. So suppose we want to like fit, let's say, stock price time series, right? So then the x-axis actually is the time, and the y-axis is like a stock price. So here, essentially, this covariance matrix or the kernel is like if the two time stamps are very close to each other, then we can also imagine that the difference in that the stock price is also going to be not that big. So that's why we can see the smoothness.
I see. So that's really, I think that's an excellent, actually, example, because that's related to the next question I was going to ask, because I was going to ask about this ordering of this index, right? Because it looks like they're not a random order, because if you just thinking about high dimensional space, there are no particular ordering of those dimensions. So, but if it's in time series, then there is a clear ordering there, right?
Yeah, so in our case, there is also no ordering. So
but if there's no ordering, how do we know that, like, if you, let's say, if you have these red points, right? Somehow when you have a red point, the nearby, the nearby axis, right? Somehow the interval got narrower. If there's no random, because that could be very independent.
Yeah, so conventionally we definitely like use 1, 2, 3, 4 to indicate the time index, like in increasing order. But even we do not know that, then suppose like we know x, which is a certain time, then if we know there's a different x, which is before x, right? So then we can utilize the distance in the time stamps to compute the kx of that new x. So it's like as long as we know the relative position, we are good.
So the assumption here is that there are some smoothness there, right? So which means when two x are very, very similar, right? Their distance is very short, then we assume that their y value should also be close.
Right.
If we don't have that relationship, then we cannot have this, narrow interval, right? Because if they're completely independent, their value.
Yeah. So they definitely should be related. And then for this particular kernel function we're using, we can see that we determine the relationship between 2 points purely based on their distance. If their relationship is like a more complicated, say maybe periodic, say like things like this, right? So if x are close, it could be like say their y are correlated, or maybe 1x here and 1x here, even though they are relatively close, their y value can be very different. In those cases, we're going to need a different this kernel function to capture the relationship. If we assume smoothness, we use this kind of kernel function purely based on their distance.
Okay.
Yeah.
Thank you.
Okay. Yeah. Thank you for all the good questions and comments. Yeah. The last thing is that this is just one example. Like this K is kind of picked by the users, how you want to model how you want to model your data. If you want your data, if you have data have very different distribution, you can choose a different K. And there is rich literature about what kind of K exists there and how to pick them. We will mention one particular one associated with neural network in the later slides. Okay, with that, let's get back to the original question we asked. So if we just compare these two pictures, one on this slice, where we have this smooth curve like interpolating 4 red points we observed, and then we have a prediction on the unobserved part, and then this kind of confidence scores on those parts as well, right? This is sort of something we wanted to do in the beginning of this nonlinear regression problem. We wanted to have those sort of curve, and then with the confidence scores around different places. So by just going through the visualization of this multivariate Gaussian and then extend it to infinite dimensional, we sort of see what's going on here. Starting from next, we are going to be more precise about what we are actually doing and then how we are going to do it for this particular problem. So let's get back to the problem itself. The problem is asking us to fit a function to our observed data. And then we have learned many ways to do that. The simplest way might be just doing a linear function, right? I will see whatever I observe, it's just a linear function of my x. And then I use this fxw as my prediction. If I want it to be more expressive, I can do basis expansion. So here, for example, I use phi x, which could be 1x and x squared. That gives me more expressiveness. So I can model complicated data distribution. Other than that, I can maybe even introduce in like the nonlinear function or so-called activation function. If I'm doing this, this is basically what the neural network does, right? Like a one-layer neural network is doing a linear transformation followed by an activation function. For all of these cases, we come up with one loss function. In this case, here is called error measure. But basically, we measure the difference between our predicted fx and the y, right? For regression, probably mean squared error is a common one. So we just square the error and then sum all the error of different data points together. So we want to minimize this loss function. This is sort of the paradigm. A different approach is a probabilistic approach. For the probabilistic approach, we change our model slightly by adding one noise term. We explicitly saying that other than my y and my prediction, I want to have a term categorize the randomness there. So commonly, this extra term, we will assume it to be distributed as a Gaussian. And then when I consider the distribution of y given my observed data x, it will also be then Gaussian, right? Just based on the linearity, it will just be a Gaussian, but with mean fx. And then if I consider all the data points I have observed, I can also come up with a likelihood of all of the data points, just multiply everything together. So I can have this likelihood. In this case, I don't need to have an explicit loss function anymore, say mean squared error. What I do is that I just turn my parameters to maximize the likelihood here. This is the probabilistic approach. The good thing about the probabilistic approach is that it can help us to interpret the error because we assumed it to be a Gaussian noise, so it's more interpretable. Also, this provides us ability to represent uncertainty. Like what we just discussed, sometimes other than the prediction, we also want to know how confident we are about the prediction. So based on the probabilistic model, there is another formulation, is the Bayesian model. We are also all very familiar with this, is that we used to have the parameters W in our model. Right now, we don't assume these are parameters anymore. We assume they are also random variables. So I'm able to put distributions on these W's. So that is when I do the parameter estimation. I'm not estimating what should be the right value of this W. Rather, I figure out the posterior probability of this W. I started with some like simple assumption, simple prior, maybe say the W is uniform. And then based on my data, I come up with this log likelihood. Putting things together, I can see what is the posterior distribution of my W. And then when I want to do prediction in the frequentist perspective, it's like I have a parameter estimated, right? Maybe based on my loss function or maximum likelihood. I just fix this parameter and then plug in the new data point X star into my model. But for the Bayesian approach is that I don't have a fixed parameter. I can still plug in this X star, but I'm going to integrate over all possible posterior distributions of my W to come up with my prediction, right? That's the Bayesian approach. Some advantage of the Bayesian approach, so it averages infinitely many models based on the posterior distribution. Here, I'm a little bit suspicious because I feel like this sentence might be a bit overclaiming, but anyway, I just took it from the lecture slides. So in this case, with this posterior distribution, we're less likely to overfit because we can always add a strong prior to the parameters, so it does not collapse to a single point, right? So we get a distribution at the end, and then typically this kind of distribution over the parameters provides more information and are more interesting than a single parameter estimate. This is the Bayesian model. So the third, so maybe slow down a little bit. So we have introduced this regular modeling approach based on the loss function. We have introduced a probabilistic approach based on the likelihood. We have introduced the Bayesian model that utilize the posterior distribution. All these three, I think we are really familiar with. The next concept, maybe some of us are not that familiar with. So I would like to give more content here. So that is parametric models versus non-parametric models. We introduce all of these concepts because Gaussian process requires us to understand this kind of concepts to fully understand what's going on. The parametric models is what we deal with every day. Most likely all the models, like maybe a mixture model of Gaussian neural networks, these things are all parametric models. You make some assumption about your data distribution, you specify some parameters there, and then you compute your parameter based on the data you observed. A non-parametric model is somehow different. In this case, we actually don't have a fixed number of parameters. In this case, the number of parameters are actually changing. Sometimes people refer to this as non-parametric models have infinitely many parameters. Personally, I found this kind of claim might be a little bit misleading because it is really what's going on is the non-parametric models, its number of parameters increases as you get more data points. So what do I mean by that? Let's look at this density estimation problem here. So if I observe some data points, I can certainly draw their histogram, which is the first plot here. Based on this histogram, I can sort of estimate what is the distribution of these data points I observed, right? So I can fit a density there. One way of doing this is through a non-parametric model, so-called Gaussian kernel density, right? So in this case, what I'm doing is actually, for this data point, I'm going to fit a Gaussian there. For this data point, I'm going to fit a Gaussian there. Basically, for each data point, I assume there is a Gaussian distribution centered around it. And then when I want to estimate the density over the whole data set, I just combine all of these Gaussians together and then normalize them to sum to 1. So that result in this nice look density here. I think this looks much better than the histogram, right? So if we compare these two diagrams, but in this case, the Gaussian kernel density estimation is a non-parametric model, because if I observe 2 more data points, I will need to add 2 more Gaussian here. That essentially increases the number of parameters I have, because each time I need a Gaussian around that data point. If I get 1,000,000 points, then the number of parameters in this case will be 1,000,000. So it's not a fixed number like parametric case. The parametric case might be, I want to fit a Gaussian to this, right? Looks like this. I just need the mean and I need the standard deviation. And then that's it. No matter how many data points there, I only estimate 2 numbers. But non-parametric is very different. So the Gaussian process is non-parametric. The third thing is to combine what we just talked about, the Bayesian approach and the non-parametric approach. This is what the Gaussian process is. It's a Bayesian non-parametric model. It allows this infinitely many number of parameters on the prior. So we're going to see that we will have a Gaussian process prior. And then based on this prior, we will model a data set. But because there are only finitely many samples in our data set, so in our data set, we only have finitely number of parameters. But in principle, we can have infinitely many. And then when we want to use this for prediction, then the extra parameters will be integrated out. So we will still be dealing with finitely many parameters. This will all become very concrete once we see the example in the incoming slides. Yeah, so just to compare the parametric Bayesian approach and the non-parametric Bayesian approach. So the parametric Bayesian approach, we have some parameter, theta. We put a prior on it, pi theta, and then we estimate the posterior of theta based on the data x we observed. Some examples can be, well, maybe we see the theta follows a Gaussian distribution, and then we observed some x also follow a Gaussian distribution. When we put them together, the posterior is also Gaussian, right? Other example, like we have a multinomial data, and then we set a Dirichlet prior on the parameters, so we will get a Dirichlet distribution. When we get to the non-parametric case, so the prior is not simply on the parameters anymore. It's on the functions it's on something more complicated. In the Gaussian process case, this more complicated thing is functions. And then when we collect the data, it's like we conditioned on these functions, but the prior we also put on these functions. So finally, the posterior distribution will be on these functions. And then this is exactly what Gaussian process is doing. Prior on functions and get a posterior distribution on functions. Let's look at one example here to get the idea of what's going on. So if we imagine this simple function, fx equals a0 plus a1x. So here we have 2 parameters. We assume they are Gaussian distributions, a0 and a1. If I draw this fx out, for each fixed a0 and a1, I will be able to draw one line, right? Maybe this line here, corresponding to one a0 and a1. If I get another set of a0 and a1, I may be able to draw another line, right, on this graph. So ultimately, for the distribution a0 and a1 follows, I'm going to get a distribution of fx, or in other words, a family of functions of this fx. So fx contains some randomness. It can be any lines we're showing here, this family of functions, and then it itself follows this Gaussian distribution. And we can even categorize it very precisely what this Gaussian distribution is, because we know we can do computations of Gaussian distributions, because this, in this case, is just a multiplication and addition. So we take 2 Gaussian 0 ones, then we can compute the mean of fx by computing the mean of a0 and a1. In this case, we get 0. We can also compute the covariance of fx just based on the covariance of a0 and a1. So I will.
Shichang, I think you probably don't have to rush. If needed, we can like spend 2 times to cover all the content here. It just,
Oh, okay. Yeah.
Want to give you a reminder. Yeah. Okay.
Okay. So yeah, thank you. Probably I was going a little bit too fast, but okay. I think this slide is enough. We have enough content here. So we have two parameters which are Gaussian distributed, and then we have one fx formed by these two parameters and the input x, and then we know f is also Gaussian distributed, right? Because it's parameters a0 plus a1 times x. And then we know for a Gaussian distribution, we only need its mean and covariance to fully categorize it, right? If we know what is the expectation of fx, and then for every two input points, we can calculate the covariance of this fxb and fxc, we know exactly like how fx looks like. So we can do this calculation accordingly. So that is saying what? That is saying we now have a distribution over functions. So this is different. I think this is something we really need to understand in order to understand Gaussian process. We used to define distribution over parameters. I have one x is Gaussian or uniform or whatever. I have parameters, so I can specify how it looks like. Right now, it's like I have this function fx. Once I plug in one x to this function, I'm going to get a corresponding value. But for the whole function itself, it's also a distribution. So if we look at where do I have the right? If we look at this picture here, it's like we may get many different curves. Each of them is a function, right? These are just two samples. These two, what I just draw are like two samples I draw from this function distribution. I may draw a new one, right? A third sample from this function distribution. But at the end, this is a distribution over all of these functions. All of these samples can be drawn from this distribution. So this is the big difference of so-called function space view versus the parameter space view. In this case, this function fx can be characterized using the mean and the covariance. Yeah, maybe I think as Yizhu pointed out, maybe I'm going too fast. Let me stop here for questions, if there are any. So please feel free to ask.
It's relatively easy for me to understand what would be the expectation of that function, right? So that's the blue line. But I still do not have the intuition to understand the kind of covariance of two functions. Can you elaborate more on this part?
Yes. So exactly. So if we look at this whole family of functions, there is one blue line here represents the mean of all of these functions. And then if we look at the covariance, still, I think it is also hard for me to understand what is the covariance between two functions. So in this case, we're just saying whenever we pick 2 points out of these functions, we are able to compute the covariance between these 2 points. And then at the end, we will just reserve this ability to compute the covariance between any 2 points. And then we say, in this case, we know the covariance between, we know the covariance of this function. Yeah. So if we go back to this case, it's already a bit messy. Maybe I use a different color. So I can specify 2 points here and here, right? And then I will be able to compute the covariance between the corresponding values. Like if this is x, then fx at this point might take these values, and fx at this point might take these values, and then these two values are correlated, and I can compute their covariance.
I see. So when x is fixed, the output is a random variable. So then if we have 2 input x, then we're going to have 2 random variables, and so that's why we can compute the covariance between those 2 random variables.
Yes, that's correct.
When will we see the definition of Gaussian process?
Very good question. I think That's next to 2 slides. Yeah. Okay. Yeah. Thank you for asking this question. I guess we can continue from there. We have this different motivation examples from one way of how to fit a nonlinear curve to some data points we observed. Another way from we first define some concepts, what is Bayesian model, what is parametric versus non-parametric, because both this perspective will come at once in the definition of Gaussian process. And this definition is a little bit different from like other definitions we have seen before. So I just want to make sure I cover these things first before the definition. Right now, we just saw like one example of fx, and we see we just said it can be a Gaussian distribution over these functions, and then we can specify the covariance between any 2 points, like the covariance between fxi and fxj. Now we can get to the actual definition of Gaussian process. Here I want to quote from Professor Richard Turner. He said that this definition is whenever someone stops you on street and asks you, what is a Gaussian process? Then you should tell him or her, okay, the Gaussian process is like this. But probably no one will ever do that. So we can look at the definition together. So the Gaussian process, it is a collection of random variables. I think this point is important. A collection of random variables, in our case, it will just be infinitely many random variables. And out of this infinitely many random variables, we say any finite number of them have a joint distribution. Like for this f, we just saw before, we saw this f is sort of this function, right? And then it have infinitely many values on it. But if we ever pick finitely many points on this curve, we see they follow a joint Gaussian distribution, right? If these two assumptions are satisfied, then we can see that this infinitely many data points, the fx, the whole curve itself is a Gaussian distribution. And then in order to categorize this whole curve, we need a mean function, and then we need a covariance function. The mean function is defined at every single point. In the previous example, as Izhou pointed out, it will be just the blue curve in the middle if the mean is 0. And the covariance function is like whenever we plug in 2 points on the curve, we are able to compute the covariance between these 2 points. Right? For example, here are 2 points, and then I can, based on this function, compute their covariance. So this defines a Gaussian process. So in other words, Gaussian process is a random function, and this random function follows a Gaussian distribution. The Gaussian distribution has a mean function and a covariance function. So is the definition clear?
Yes, it's clear to me.
Okay. Okay, thank you. If the definition is clear, I hope we can see the connection to those concepts we just introduced, right? So we introduced a nonparametric model. In this case, if we want to categorize this whole function f, we will need infinitely many parameters. So we cannot actually have infinitely many parameters, so we choose to have these functions. Whenever I plug in a new value, it can give me the result. So the mean function and the covariance function. With this definition, let's look at another
in this
example.
particular definition, there is no restriction or constraints on the form of the covariance kernel or the mean function, right?
No restriction. So I guess for the covariance, it needs to be it may require to be a kernel function. At least in practice, people use positive semi-definite kernel functions. So because it's a
covariance, of course, if it is a covariance, of course, it is positive semi-definite.
Right.
For sure. But that is pretty much it. There is no other restriction.
I think that's the only restriction.
Okay, thank you.
Yeah. Okay, so maybe we look at another example so things can become even clearer, hopefully. The simple linear basis function model we showed in several slides ago. We say that we'll give you an input x, you may define this phi x, might be 1x and x squared, and you're going to use this as your basis to fit your model, right? But if in this case, we also define a Gaussian distribution on our parameters w, then this fxw becomes a Gaussian process as well. So it's just like the a0 plus a1x case. We can, because this parameter is Gaussian, we can compute its mean. Because this is Gaussian and this calculation is linear, we know f is also Gaussian. We can compute its mean and we can compute its variance. So we get this mean function and this covariance function that fully specify f. So our conclusion is that, well, fxw is a Gaussian process, and then I have this mean function equals 0, and then this covariance function equals this form, right? So so some good things about the Gaussian process is that we used to be interested in the parameters in a parametric model. Say we define some parameters and then we want to estimate them. So, and then in the Gaussian process case,
when we try to model our function as a linear combination of basis functions, are there any other ways to create a Gaussian process model instead of assuming that the weights are Gaussian distributed?
Right. So there are actually two different ways to create a Gaussian distribution. So we gave two examples. One is the one on previous slides, f equals a0 plus a1x. One is this one here, f equals w transpose phi x. Both of these are so-called explicit way of creating Gaussian process. So you specify your parameter, you specify a formula for calculating f based on your parameter and your data. And then after some derivation, you show this f has Gaussian distribution, right? So this is one way. Another way is more like an implicit way of specifying Gaussian distribution. So that's like, I don't make any assumption of any parameters at all. I just say I have fx. I don't know what are the parameters there. I just specify one mean function, and then I just specify one kernel function. That's it. That I say this is a Gaussian This is a Gaussian process with mean function mx and a kernel function kxi xj. That still works.
If you do that, then we don't know what the basis functions are, right?
We don't know. Yeah. So in the
simply specifying the functions of m and k's, the kernel function and the mean function, and
right.
we have other things we have no idea what those are.
Right. Later on, we
and
will see.
In those cases, the kernel functions are simply based on the functions of the distance between xi and xj, as opposed to can be any arbitrary kernel.
It depends how you want to model, how you want to specify your model. Later on, we will see like all the inductive bias you can put into your Gaussian process is through this kernel function. So if you use different forms of Gaussian kernel function, it may depend on the distance, it may depend on something else, right? And then there are also some hyperparameters inside of this kernel function, and then you can also tune those parameters to get different kernels.
Okay, can we, so I want to make some I want to get better connection between this model of linear combination of the basis functions and the more general model, which is just simply giving us directly the m functions and kernel functions.
Mm-hmm.
So there should be, so now the derivation that you show, can you go over this a little bit more carefully? The expectation and mx and 0, are they assumptions or are they derived results? Exactly what are they?
Yeah. So for sure. So I'm going to clean the screen a little bit. Yeah.
So what
So
I'm trying to get is when we assume this model where we assume certain kinds of linear basis the basis functions, and then we assume that our function is living in a space of linear combination of these basis functions, and the space is characterized by the weights are distributed by the normal distribution. In those cases, I want to see what are the functional forms of the mean functions and kernel functions. That's what I'm trying to figure out.
okay, great summary of the question setup. And then let me answer that. So here, above this line are our assumptions. Below this line are the derived results. Okay. So
can you explain the first layer? Can you explain those derivations?
Yeah. So all we assumed is that fx is like this linear dot product between our parameter and the basis, and then we put a prior on these parameters, and the derivations is like this.
So your
We
expectation is over the different weight distributions, right? So random
yeah,
variables are just W, right? So expectation is done over the W.
So when we do this two derivations of the mean and the covariance, we can think of x as a fixed value. Right. So no randomness in x. So right. Ultimately, we want to say this is expectation over the function, but the randomness really is inside the parameter itself. Yeah. Right. Okay. So this is just a two equivalent expression. So we just write out the fx, which is W transpose phi x, right? And then because we know we can think of this phi x as fixed, we can take it out of the expectation. Then it will just be expectation over W transpose, and then which will be 0. So I guess the expectation part is simple, right?
It's because the normal distribution is centered around 0.
That's our assumption. We assume we assume that the normal distribution to be centered around 0. If we assume something else, if we assume this here, I don't know, maybe the identity matrix, then this will be the identity matrix.
So somehow here the assumption, that assumption, the weight is normal distribution, somehow heavily biases, puts a lot of heavy inductive bias towards where we have almost all basis functions are kind of close to 0. Their weights.
Their weights are close to
weights are close to 0.
If the covariance is very small, if this is very small, yes, it means the prior distribution on these weights are centered around 0. But it can also be the case that this is very flat, right? So the normal is close to a uniform.
Right.
That's also possible. Yeah.
Can you show the derivation of the covariance?
Yeah, sure. So yeah, so this mean part is simple, right? So for the covariance part, this is also just two equivalent notations, and then yeah, so maybe I remind you the formula for computing the covariance between two random variables. That's like EXY minus EXEY. So it's just the expectation of the multiplication minus the multiplication of expectation. Okay, sounds like a tongue twist, but it's this formula here. So we are interested in two data points, fxi and fxj. So according to the formula of covariance, it's just this one here, right? For the second one, because we know each of them is has expectation 0 centered around 0. So this term will just vanish. So we get minus 0 here. For this term, we can also plug in fx equals right here, W transpose phi x. And then we take x out of the expectation because there's no randomness in x. So we result in this one. And then the formula here in the middle is just the formula for covariance. Maybe I specify one more right, minus step here. Okay, so this equals this, but because this term also vanishes.
So what's the
So that's how we get that.
dimensionality of fxi and xi? Because we have the W transpose, but somehow in that EFXI and FXJ, that's not. I mean, we need to somehow put a transpose on the first FXI.
So it's a single dimension, right? So if phi x equals 1x x squared, then the W probably is W1, W2, W3. If we do dot product, it's just a weighted average of these three things. So it's a single dimension.
I see. Okay.
Yeah. So this one is single dimension. This one is single dimension, but we take out the x out of the expectation, and then what's left here is like a 3 by 3 in this case, 3 by 3 matrix.
So then somehow the corner value then, no, the corner, yeah, this is the corner, covariance is the corner. So the corner value depends on the values of that function, the basis functions at that particular points. If those values are high, somehow the overall covariance is somehow assumed to be high, as long as those are reasonably aligned well with a W covariance matrix.
So are you saying that if some entry of this covariance matrix is high, then the covariance between fxi and xj is also high?
I'm just trying to figure out what are the relationships of that covariance corner to the values of the basis functions at that particular points, xi and xj. So if you look at the vector of phi x, it will have this one value and x value and x squared value. So when those function values become large, somehow the covariance becomes large as well.
Let me see if that is true. When those values becomes large, the covariance becomes large. Yes. Yeah.
So what are the, I see a formula, but I don't know what this covariance corner look like. That is something that I don't know very well. It is definitely not dependent on the distance of xi and xj only, clearly.
Okay, maybe I just, it's a bit messy, so I will just get rid of this first. So if we think about a simple case, if phi x just equals x, right? Then this will be x transpose or xi xj, right?
What is x? X is are you talking about phi x, phi of x, or are you talking about what is x?
Yeah, so I try to think about like a simple case of to see if we can get the meaning of this covariance kernel in this case. So I say, like, if we assume this basis function is doing nothing, the identity function phi x equals x. If that's the case,
okay.
the formula will be further simplified to this one, right? And then the yeah, in that case, we actually don't need a transpose because it's just a single dimensional, right? So this covariance matrix is also just one value, right? This sigma W is also just one value. In that case, if this gets large, well, yeah, it can also get large if xi and xj have the same sign. And also similar, if this gets large, the covariance will also get large.
what I'm trying to understand is the following. So, of course, when let's say I have a data, right? And I want to somehow figure out those, predict whatever missing value somewhere in between, somehow do some interpolation or whatever. So let's say I want to do, I learned about the Gaussian process. So now I want to use the Gaussian process to somehow predict whatever missing values based on the data that I have, right? And of course, in that case, we can pick some linear basis function, some basis functions, set of basis functions. Let's say it's a polynomial function, then I will assume these basis functions that are like 1x, then x squared, etc. And then I have to make an assumption, right? So maybe there is a good reason. For now, even that is problematic, but let's say there is a good reason to assume that linear polynomial is a good basis functions to choose. But in order to use this particular model where the weights are Gaussian distributed, somehow I want to have some justification of whether that is a good modeling or not. Because if somehow that is if I'm not convinced, or if it is not a good model, then however fancy Gaussian process might be, whatever prediction that I get from that modeling is complete junk. So what I'm trying to see is exactly under what scenarios this kind of assumption about the way it is Gaussian distributed, that is a valid assumption, that is a reasonable assumption. Right now, I don't have any of that intuition right now. So I'm just trying to figure out, by looking at some of these different formulations and formula, I'm trying to figure out what are the characteristics of this set of functions this particular function space has, so that, in those scenarios, that function space or that kind of modeling is a reasonable choice. And in those scenarios, those kinds of modeling is a reasonable scenario. But right now, unfortunately, I don't have that. And even after going through all these derivations, I still have a little bit of hard time of how I can convince myself that, yeah, this is a good model. I can just assume that the weights are Gaussian distributed.
So, yeah, so if your question is about, say, let's forget about the non-parametric or whatever. So here we have a model, we have some parameters, and then we want to use a Bayesian approach to put some prior on this on the parameters, and then estimate the posterior, right? So as simple as like whatever Bayesian model we can think of. I think your question is about whether the Gaussian prior is a reasonable prior on the parameters I care about, right?
Yep.
So I think without any prior knowledge of how the prior looks like, I think Gaussian distribution is a reasonable prior, right? I think so. So when choosing, when choosing priors, there are like different criterions people can follow. Say we choose the conjugate prior, so we make the calculation simpler. I don't want to introduce any bias, then I may use a say uniform prior. Say I know nothing about my parameter, and then in this case we are introducing a Gaussian prior, saying that okay, my parameters may be around 0 in this case with certain covariance matrix. If the based on the particular way you are forming your model, then this is an unrealistic assumption. Then yeah, maybe the model won't do very well. But I think at this point,
there is a complex interaction between the choice of the basis functions and the prior assumption that we place on the weight distribution. Because of course, using 1 and x squared as our basis functions is one way of doing it. But under the same functional space, we can instead use like 1 and x minus 1 and x squared plus 2x minus 5. Those are also reasonable basis functions that span over the same set of functions. And in those cases, what assumption I make on the parameters, of course, in these two different choices of the basis functions, we can assume that in both cases, the weights are Gaussian distributed, but those assumptions lead to completely different kind of modeling that I do on the functional space, because my choices of the basis functions are very different. So I hope I can get some ideas about what are the general shapes of the functions that somehow I imagine and how those general kind of expectation is translated into these assumptions that are incorporated into this Gaussian modeling. That mapping is not very, it's just complete almost magic to me. Or just assuming that this is a Gaussian, normal Gaussian distribution sounds like too much of a leap of faith to me. Because I cannot just do that.
Okay, so I guess I have some visualizations. Also, I want to point out one thing that might cause some confusion to some extent. So I totally agree that this model, particular model we are showing on this page, is not a good model. Why it is not a good model? Because our mean function always gives us 0. That's some like a ridiculous result, right? So if we look at this sort of graph here, so if the mean function is always 0, it means the samples we draw will always be curves like this, centered around 0. If our data points are all around here, or like even here, then this model will completely fail, right? Like it will have huge bias and never capture how the data is distributed. So that's why we need two things. We need the mean function. We need the covariance. We need the covariance kernel to categorize our function. That's one thing I want to say. This 0 here is not a reasonable choice. The second thing is that I have some visualizations. Let me look for them that we can check. Right, yeah, probably this one. So when we do only the Gaussian priors, so yeah, in this case, we have this input X, and then we want to fit the prior. It is rather random, like all different colors here showing like different function samples we can draw from this prior. After we observe some input X, we can draw from the posterior distribution, like which is showing on the right here. So here, if we assume some like local smoothness, if we use the kernel function, I guess in this case they use the kernel function based on the distance. So if we assume the kernel function is based on distance, and then we have some local smoothness, it's like saying, I don't know, maybe you cannot see here. This crosses indicates the data points I observe. This is just saying, okay, if I have this, let's say if I have this data point with its X value and the Y value, and then why I want to use Gaussian is that I want to say I have another data point here. They two are like the red one and the blue one, they are joint Gaussian, right? They are jointly two-dimensional Gaussian. So when they are highly correlated, the blue one is a fixed value in this case. Then the red one maybe only like have a very small random interval. It can oscillate, right? So it's really based on this assumption that I can assume things are Gaussian. So before I observe everything, the prior showing on the left, this picture indeed doesn't tell us much. It will just be a random function. But if we observe some points and then we have some other points, we consider these 2 points as joint Gaussian, and then the high covariance between these two can tell us something about the unobserved one.
Okay, thank you. Let's continue.
Yeah.
Okay.
Personally, I agree with that part, right? So the prior is only important only when we don't have enough like observed data. But once we have enough data, then actually we can really update our belief. And by the way, if you go back to the slide, I think I have a very good understanding on the formula now, I think. Yes, yeah, so
this one?
Yeah, so if you look at that, right? So if we consider a spatial case like sigma W equals to an identity matrix, right? So in this case, actually, we just try to use the inner product of the vector, kind of the basis vector, right? So for xi and xj, we just try to compute the inner product. So if they are quite close to each other under that basis, right? So then we say, oh, those two data points are close to each other. So that's why we are going to have this y value output from xi and xj also very close to each other. So in other words, just to try to guarantee the smoothness. But how to define this the similarity between xi and xj, that's the main point. And if we go to a more general case, let's assume this sigma w is no longer identity matrix. It's a general covariance matrix. It's just a scaled version, right? It's just to try to also calculate the interaction between different dimensions of those bases. So then we have a more complicated kind of score. Yeah, it's very similar to, for example, the neural tensor network, right? So it's just to try to kind of rescale the importance of each dimension and try to also capture the interaction among different dimensions. So it's kind of more general, more complicated way to compute whether this xi point and xj point, they're close to each other or not. So that's my understanding to this formula.
Yeah, thank you for the comment. Okay, Zhang, I feel like you are not satisfied with my answer just now. So,
Oh, it's fine. No, it's fine.
Okay.
No, it's fine. I will never be satisfied completely. So having a little bit of unsatisfaction is fine. That's how I am. So.
Okay. I mean, I'm also learning this. I guess I learned Gaussian process like about I used to have some shallow understanding, as I said, but in order to prepare this presentation, I just started like 10 days ago. So if any of you have any like I don't know, comments or opinions, ideas you want to discuss, I'm very happy to further discuss these things offline.
Yeah,
but
Shichang,
yeah,
I'm not sure whether you have some slides about like to show how the difference of the kernel function can cause a very different behavior of that curve. So personally, I think that sort of visualization really helps me a lot. I think there's I think I read some like blog, right? So yeah, in that blog, they really kind of show different kernel function, and then they also tells you, okay, at which circumstances you should use this kind of kernel because of this property. Yeah, probably if we have that, then we will gain that kind of intuition.
Right. Yeah, I think that's a really good point. So for most of this presentation, everything is based on that Gaussian kernel. So the formula is this one here. So basically based on the distance between two data points. So if that is the case, basically it's the same kernel function, but we use some hyperparameters to control like the scale of this function. I think what you're saying is that we can have some more complicated kernel functions that is not necessarily based on this distance. Like maybe as the example I gave before, we have this periodical functions we want to model, then only distance-based may not be a very good idea, right? Seems like
yeah, exactly. You remind me. I think in that blog, unfortunately, I could not find it right now. So they show that if you want to have this like a periodic behavior, then what kind of kernel you need to have. That's exactly one of the examples given in that blog.
Right. I also read about this, but unfortunately, I don't have a visualization now. But I guess I need to take one more reading group to finish all this material. So I will make sure to include those next time. But if we only look at like a single kernel function with different hyperparameters, which I prepared, it's like the comparison with these two functions versus these two functions, right? We can see through the kernel function, we can have some sort of control of our model, right? So in this case, we control the scale of say if in this case if we increase the parameter L, that means each data point will depends on points that is very far away from it. So if we look at the formula here, if L becomes very large, that means even x1 and x2 are very far away from each other. And then we can sort of have an influence between these two data points. So in this case, when L is small, things are more oscillating. In this case, when L is large, things are more smooth. And then if we change the kernel function completely, we can use that new model to model other data distributions. So there are two things. If we fix a kernel function, the parameters inside the kernel function, like L, we can learn it as we learn any other like models, neural networks, any other models, like we learn those parameters, right, by maximizing the likelihood. If we choose to change a completely new kernel function, this can also be a design choice or like a inductive bias we want to inject into our model. There is really rich literature about many different kernel functions, and for each different situations, what we should use, right? There is flexibility there.
Hold on, can we go back to that graph?
Sorry, this one?
Yeah, that
this one?
That one.
Okay.
How do we sample from Gaussian process prior? How are those graphs generated?
You mean only the prior on the left hand side?
Oh, left and right.
Yeah.
Well,
So
left with left.
So if it is just say fx equals a0 plus a1x, I just need to sample a0 and a1, right? That's sample from two Gaussian. That's easy.
This is based on the kernel function as opposed to linear combinations or Gaussian priors on the weights of the linear basis function. No, this one I can do it. So
Yeah.
with the Gaussian prior, then that I can do. But what about?
So if I just have these things, right? If I just have these functions, right? So
yeah.
So I can also get a bunch of x, right? So sample a bunch of x and plug each one into this M and plug each pair into this K.
Oh, it's not just a pair. It's just, is it a pair? Is it a pair or is it multidimensional? It's multidimensional, right? No.
So if this is xi, this is xj, I can compute kxi xj, right?
This is a k is a, if there are, let's say, 10 data points, isn't k isn't k
100?
Yeah, 110 yeah, 10 by 10 100? No.
10 by 10 100?
No, 10 by 10, 10 by 10, which
10
is
by,
100.
yeah, 10 by 10, 10 by 10, yeah, which is 100, yeah.
So that is the matrix.
Yes, that is. If I have 10x, I sample 10x, then k is like a 10 by 10 matrix.
And then given that, what do? We just do the Gaussian sampling from that dimension
yeah.
10 Gaussian distribution.
Let me see.
Yeah, I think so. That's what you do.
Yeah.
Okay. Then it's okay. Then it's clear. Okay. Thank you.
Yeah. So although the visualization looks like a smooth function, infinite dimensional, but we still pick some sample points, right? Okay. Let me get back to here. Yeah, very nice discussion. I like this. I feel like some of our previous reading groups, sometimes I enjoy this interaction more than a single person like me here just lecturing, because this also helped me to learn stuff. So maybe I will see where is a good stopping point, and then maybe we can continue next time. So we discussed a lot about how to interpret Gaussian process, but here are 2 points that Eric Xing emphasized. So I want to bring this up as well. So in the old models like neural network and what else, we were really focused on the weights or the parameters in the model. So whenever we think about the data or we think about how to make prediction, we say, okay, I first estimate some parameters, I fix them, new data comes in, I just do whatever calculation I need to do between my parameter and data, right? Say maybe W transpose X, right? I estimate one W, I put it there, comes a new X, I do W transpose X, that's it. And then for the Gaussian process, it's like we're looking things from like a different way. We want to directly specify the function itself. I'm saying that there is no like parameter, or like at least the parameters are implicitly. I want to get an intuition of this function. So whenever I have a new X, I plug it into this function, I will be able to get it. And then this also allows us to do generalization, and then we can control everything using our kernel functions, as we just discussed. A single kernel function, we can control its hyperparameter. For different data distribution, we can control it by using different kernel functions. And then with this, it's really the flexibility we get with the Gaussian process model. And that's actually the only way you can, maybe let me see. Yeah, that's actually all the information you want to put into your Gaussian process model, because other than the kernel function, everything will depend on the data you get. Turns out Gaussian process can also be visualized as a graphical model. So in this case, the X1, X2, Xc, these are things we observed. The X star, Y star, so X star is something, the test data, something we want to predict. Y star is what we want to predict. So if we draw everything as this graphical model, it used to be like what? It used to be, we just build a graphical model using all the X and all this Y, and then we want to estimate this F star, which is a function with all the estimated parameters, which is the function we want to use for prediction. That's the other parametric model. And then in that case, once we get this F star, once F star is known, it's like we conditioned on this F star, then all of these data points, we have already utilized the information in it. So Y star will be dependent from all this stuff, because the information are already captured inside F star. But for this Gaussian process, like this non-parametric model, is that we always think about all of this are dependent on each other. Whenever there is a new X comes and I need to predict its Y, I will sort of collect the information from all of my X and Y's again, and then do the prediction of my Y. So I never get rid of my data, because each data point I had is sort of my parameter in my model. Oh my God, there is a question in the chat 35 minutes ago that I didn't see. Okay. Okay, so the question is like, can you use central limit theorem to get a Gaussian process from some other random processes? To this question, actually, I don't know the answer. Okay, so yeah, I will also look up this question, and Fred, feel free to discuss with me offline, I guess. Fred and we already had several round of discussions about Gaussian process and some other stuff, and I think we can also handle this question offline.
This
sorry for
model that you showed there, that one is not really the model that you verbally explained, because the connections, the dependencies between these functions are only kind of one-dimensional. So it's not like complete graph. It's kind of a serial chain.
Oh, yeah.
Is it just a matter of your the graph is?
Yeah, I think that's a really good point. Here it says it's a Gaussian field. I guess a Gaussian field means all of this F on this very thick black line are like interconnected with each other. Yeah.
So it's a complete graph.
Yeah. Just to fit it to the slide. Yeah.
Okay.
Yeah. Thank you so much for the reminding that this is not a sequential. There's no sequential information. So we have everything dependent on each other. Okay. Yeah. I have something we can quickly go over, and then after that, I think we can maybe stop there. So this is the older slide. Back to the sort of the motivating example I give at the very beginning. So we were saying that we want to have this continuous function, and then with infinitely many x, and the sum of the x, y values we observed, like these 4 points here, right? So this is a problem we started with. And then we introduced a parametric model and a non-parametric model. So for parametric model, we just imagine there is this fx and some parameter theta we want to estimate. And then there is this noise term we plug to fx. I guess this is also related to a very early question Zhang asked, is that why do we have this sigma y here? For the Euro parametric model setup, we also have this term because we are not saying what we predict this fx is what the y value is. We also allow some noise there. In the non-parametric case, I guess we have a corresponding term. So actually, when we can have this mean function and kernel function to set up a Gaussian process model, but we are still actually haven't explicitly mentioned how do we use the Gaussian model, right? And then how do we use it to solve this regression problem we asked in the very beginning? So this is a question I'm going to show next. So we have this setup y equals fx plus this noise, and then we can put some distribution on this noise, see normal 0, 1. Then we can also place this Gaussian prior on all possible fx functions. So here there are really two different randomness. One is that this fx we wanted to use to do prediction for x. The other one is the explicit noise term we included in the y function. So for this, what's going on? For this noise term, we have this Gaussian noise placed on it, this prior. For this fx, as we have been talking along the way, there can be a prior on functions, which is our Gaussian process placed on it. And then this Gaussian process, for simplicity, we assume it has mean 0. So we only need one kernel function to specify this prior. Then this is how we set up the Gaussian regression model. So yeah, so then when we look at the distribution of y, there are actually two terms. One comes from this covariance kernel. One comes from this explicit noise term. Then if it is infinite dimensional, right? So if we still imagine the covariance as a matrix, not as a function, then how can we represent this infinity by infinity matrix in our model? More explicitly, how can we do such representation or calculation using a computer, right? The point is that we integrate out all the unnecessary parameters. Like when I first introduced the Bayesian nonparametric model, let me see. When I first introduced the Bayesian nonparametric model, I mentioned 3 points. Okay, maybe I can. Where is it? Oh, right here. So we allow, if we look at here, we allow infinite number of parameters as our prior. But when we actually use it, because there are only finitely many data points in our data set. For each data point, it will only result in one parameter. And for all the other extra parameters, we will integrate them out. So we still get finitely many parameters that we can use in our actual model. So that's for this kind of thing, we actually need a good property of Gaussian, because if it is not Gaussian, then this kind of integration can be very hard. But because we assumed everything, this infinitely many things, they are a joint Gaussian. So this integration actually becomes super easy. Because if I have a y1 and y2, there are infinitely many y2, and I want to integrate out, I know the marginal distribution over y1 is still Gaussian. So I only need to look at the mean of those dimensions in y1 and the covariance of those dimensions in y1. So I just read out these two corner part of these two infinite many long matrix, then I get the marginal distribution, right? For say I have 100 data points in my data set, I will just get this 100 dimensional distribution over y1. Then when I observe some new y's, in this case, say, okay, so in this case, the observed ones are called y2 and the unobserved ones are called y1. Then I have 7 dimensions in total. 4 of them are observed. So I can predict the other 3, right? So this is how I do the prediction. I compute the conditional distribution of the unobserved one conditioned on the observed one. Because of the nice property of Gaussian, I know the conditional distribution is also Gaussian. So this formula, I won't do the derivation. You can look it up, just type conditional distribution of Gaussian in Google. You can see it. Yeah. So we will directly take this for granted. And then based on this, although we won't do the derivation, we can look at what's going on here. Originally, if we didn't observe anything, we know nothing about this. Also, if we didn't observe everything, we have this prior mean of y1, which is a, but still we include some linear function, right? This is just a 2 matrix multiplied together and then minus some vector. So we include a linear function of y2 to the mean of the posterior mean of y1. So this is saying, because I observed the y2, now my prediction of y1 is something linear in what I observed already. If we look at the covariance matrix, still we have the prior covariance of y1, which is just this a here. But because I observed y2 with these 4 dimensions, I can also calculate one more term. So this term makes my covariance matrix sort of smaller, right? Because I have more confidence, I have more certainty at these 4 points. So because these 4 points and the 3 unobserved points are correlated to each other, so I'm able to do some uncertainty reduction. So I subtract something from my prior covariance. This is how we do the prediction. Once these 3 test points comes, all of the 7 points becomes a joint distribution. And then I use the conditional Gaussian to figure out these 3 unknown points. Okay.
Can you
maybe
go back?
This page or previous page?
Yeah, this one.
Okay.
AB, lowercase ab, uppercase ABC, are they calculated from data, or are some part of it is?
They are priors. They are
those
priors.
are priors. Those
yes,
are priors.
Yes.
AB and ABBC, these are all our priors.
Right. Yeah.
I see. And then, okay. And then when you go to the predictive mean formula, from the first line to the second line, why do A and B disappear? They are lowercase a and b.
Oh, I think that's because for simplicity, we assumed them to be 0.
Oh, those are, you're assuming that those are 0. Okay, that is okay.
Yeah.
Okay.
Yeah.
Just an assumption. Okay.
Yeah. So like we have been doing for the mean because we want to focus on the kernel function and covariance, for the mean, we always assume to be 0, the prior mean. Okay. Yeah.
Thank you.
I think this might be a good place to stop. And then, yeah, if there are any questions, feel free to ask. I'm very happy to discuss all of this. So yeah, definitely speak up.
Yeah, that's a great discussion. Thank you, Shichang.
Yeah, thank you. Thank you for allowing me to take one more reading group. I remember last time when I was presenting paper, it also took 2 reading groups. So I will definitely get that different kernel function visualizations next time, and then we will finish what's left next time. Okay. Thank you, everyone. If you have more questions, we can also discuss offline if you like. Otherwise, maybe I will.
Maybe I want to ask this final question.
Yeah, definitely.
In terms of the covariance formula, so predictive mean, when you talk about the predictive mean depends on the data, Y2, right? So that is fine. That's good. But somehow predictive covariance doesn't depend on the data. It's just based on our prior. Our prior determines our predictive covariance. That seems to be a quite interesting implication of like what are the expressive power of this particular model. Because somehow this model doesn't really control, or our data doesn't guide us in terms of how much of a covariance we somehow want to enforce between 2 different data points. It's just purely determined by our model. Seems that way.
Oh, so yeah, sorry, I think this is a really good point. So because we observed Y2, right? And then because we observed the X values corresponding to Y1s, right? And then if we use the kernel function, we can actually calculate these terms. So do you see what I'm saying? So because for the kernel functions, let's say Y21 and Y22, like these 2 data points, maybe these 2. If I plug them into the kernel function, I can calculate their, I plug in this X21, X22, I can calculate the covariance between these 2 points, right?
Yeah.
So I think once things are observed, then we actually know what each of this looks like.
Didn't you say B and C's are already given as a prior? No? Yeah.
So this is a very good question. So let me think about it.
But I think now I understand. Now I think I understand. Predictive covariance. Here, predictive mean we are trying to predict Y1, which we have never observed. And then we try to predict Y1 purely based on the nearby values, whatever we observed, and their covariance relationship to those observed variables. So it is reasonable that Y2 plays a role in predicting the Y1 value. So that is fine. But in terms of covariance, because we have never seen Y1, of course, there is no way to somehow use Y2 to somehow predict the covariance. So the fact that Y2 plays a role in predictive mean, but not in predictive covariance, seems to make intuitive sense to me now. Because we never observed Y1. And there is no way to somehow improve my covariance when I have never seen Y1. Covariance requires some observation of both a Y1 and Y2. But mean, based on the covariance understanding, covariance model, using Y2, I can influence Y1. So that is possible. But covariance seems to be impossible. So that is why it's almost kind of.
So for covariance, we can also use we can also figure out the influence of Y2 on Y1, right? Because we know the X. So Y is something we try to.
So that is the covariance. That is a covariance assumption. but we cannot
Yeah.
improve that assumption because we never observed Y1. If we do observe Y1, then we can improve that assumption of the covariance. But we never observe Y1, so there is no way that we can somehow change our covariance assumption, because we need observation of the covariance relationship. Then we can refine it.
Yeah, to me, the covariance is determined by somehow the relative position of x1, x2.
Yeah, original
Mhm.
value.
Yeah, yeah.
Okay, thank you. Thank you very much.
Okay.
Yeah,
Okay.
thank
Thank
you.
you. Thank you for
Bye.
all the questions. Bye.
Bye-bye.